In this lecture, we are going to look at how to use the t-distribution to model our returns in code. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. Basically, we're going to follow all the same steps as we did on our previous script, except that now we're going to do them with the t-distribution instead of the normal distribution. To recap, we're going to plot a histogram alongside a plot of the PDF of a t-distribution, where the parameters of the t-distribution are the parameters of best fit given the data. Next, we'll look at the QQ plot of the data against the same t-distribution. Then we'll repeat those two steps with the log returns instead of the actual returns. So first, we're going to import the t module from scipy.stats. I put a comment here to be careful because, as you know, in programming we often like to use short variable names. It would be very easy to overwrite the variable t with something else like a loop index. So make sure that when you are using the t-distribution that you don't use the letter t for anything else. Next, I'm going to do the same thing I did in the previous script, where I create 100 evenly spaced points between the minimum value and the maximum value to represent the x-axis of our plot. Next, I'm going to call t.fit to get the parameters of the best fitting t-distribution to our returns data. I've assigned these to a variable called params. If we print out params, we can see that it's a tuple containing 3 values. Now, it's not clear what these 3 values represent. In fact, the documentation doesn't explain what they are, so it's up to us to find out. Let's assume that they are in the order of degrees of freedom, location, and scale, and then if we're wrong, then our plot will look bad. So next we're going to get the PDF of the t-distribution using these parameters. As before, the first argument is the x values, and the next few arguments are the parameters. Next, we plot the PDF and the histogram side by side using the same code as before. So clearly this is very exciting. We see that the t-distribution is a much better fit than the normal distribution. The peak of the distribution almost perfectly captures the peak of the data. Furthermore, there is no gap in the shoulders of the distribution as there was with the normal. And that's because that weight is being distributed across the tails and the head. The next thing we want to do is the QQ plot. So let's try stats models first. Now, you might assume given the documentation that we can simply pass in the t module for the dist argument. The reason we didn't need to pass in anything before is because the default is the normal distribution. Now that we want to compare to a distribution other than the normal, we need to specify which distribution explicitly. But unfortunately, we get an error. Notice, it's not because we passed in the wrong thing. In fact, the documentation tells us to pass in something exactly like this. As you can see, it's actually calling functions on the module that we passed in, which means that what we passed in at least has the correct function names. So if we look closely, it looks like we're trying to call a function ppf, but it's missing an argument for df, which is the degrees of freedom. By the way, you also want to be careful when you're working with variables called df, because we often use df for degrees of freedom, in addition to often using df for data frames. In any case, this makes complete sense. It's just a very strange API. The reason it's complaining is because all of the scipy functions for the t-distribution require an argument for the degrees of freedom. We see this explicitly when we look at the documentation. Distributions like the normal only have a location and scale parameter, so when we pass in the normal, QQ-plot works just fine. To get you more comfortable with this idea, think of another distribution like the exponential. If we check out the documentation for the exponential, we see again that it only has parameters for the location and scale. There are no extra required parameters. Now, you might say, this is because we're trying to mix up scipy and stats models. Maybe it will work if we use pure scipy. So let's try the same thing again with the probplot function from scipy. Again, we pass in the value t for the argument dist. Note that this argument also typically accepts strings, so I can pass in the string t instead of the module t. Basically, the string you pass in just has to match the name of the module. Unfortunately, we see that we get pretty much the same error, missing one required positional argument, df. So what can we do? Well, we can give these functions the arguments they expect. Specifically, they want to be able to call functions inside the t module, but without the df argument. We can accomplish this by creating our own custom class. I'm going to call it myT. Inside this class, I'm going to first declare a constructor, which takes in one argument, df. This is going to store df as an instance variable so that it never has to be passed in when we call any subsequent function. The nice thing about Python is that the syntax is the same everywhere. We can call t.fit and t.ppf, and it doesn't matter that t is an object or a module. So that's why this works. Even though the original t is a module, and what we are doing is creating an object, these functions are accessed using the exact same syntax. So next, I declare a function called fit, which simply calls t.fit. Note that this doesn't actually require a df parameter, but it's called by the qqplot function, so it's necessary to implement. Next is the important one, the ppf function. This one is only allowed to take in a location and scale, but internally we add the df parameter by passing in self.df. So if we try sm.qqplot again, but passing in an object of type myT with the degrees of freedom we found earlier, we see that this now works. And of course, as our density plot suggested, the t distribution is quite a good fit. The points are now not diverging at the ends any longer. Next, we can do the same exercise, but on the log returns. Again, the first thing we do is create 100 evenly spaced points between the minimum and maximum to go along the x-axis of our chart. Next, we call t.fit to get the parameters for our t distribution. Next, we assign the parameters to variables called df, loc, and scale. Next, we grab the values of the PDF by calling t.pdf, passing in our data and our parameters. Next, we plot the histogram of the log returns along with the PDF, again observing that this is a much better fit to the data. Finally, we create our qqplot, again using a myT object for the dist argument. As you can see, this is again an excellent fit, which is not surprising since the log returns are very close to the returns.